So let's go and start lecture 10, function approximation. So you can, instead of tabular methods, you can use a function to approximate either the v state value function or the q, the action value function. So for the q, you can either use a as an input, or you can compute all possible Q functions for all possible actions. If you use neural networks, uh, it corresponds to having A as the input and producing one QSA, or producing all QSAs for all possible A's. So I think Carla mentioned this before. Because you need all the AIs for all A's for computing the argmax A, the greedy policy. So the latter approach is predominant in these days. So the mean squared error, I mentioned this before in the imitation learning lecture, but just to reiterate, suppose we have a real value function v pi, the blue curve, and we use a linear function to approximate the v pi. V hat is the estimated value function. So we want to minimize the value error, which is expectation over with expectation under policy pi for the squared difference between v pi and v hat. So expectation is taking a sum of all the states with the weighting factor mu as probability distribution of state S when following policy pi. And sum over all S of mu S is equal to 1. So this is just the definition of expectation. So we want to minimize this value error. We can use a gradient descent. So here the x-axis corresponds to the weight vector W. So we typically use the bold letter to represent a vector, and a non-bold letter to represent a scalar. So in general, it should be a bold vector, especially for neural networks. There may be millions of weights in a deep neural network. But the cost function is a scalar, a loss. And every time you follow the gradient, gradient is a symbol here, represents a vector of partial j over partial W1, partial j over partial W2. Okay, so the W1, W2s are not vectors. These are elements. These are elements of the vector, weight vector. And the alpha is the step size parameter. Typically, it's gradually reduced as you run the gradient descent. So, so here's the gradient descent for minimizing the mean squared value error we saw before. First, we can take the gradient operator inside the sum because it's taking gradient with regard to the weight vector W. So it's not the sum over mu is not a function of W. So you can take it inside, and then you can gradient of the square is 2 times this value, and then gradient over the v hat. That's just the chain rule. And then with the weight update, you have this formula here. So this is not practical to evaluate for a large number of states. We do this by sampling again. So we replace this expectation by sampling to have a stochastic gradient descent. So at every step, you update W based on a single new state and its value v pi. So now notice first we remove this guy because we're evaluating the expectation by sampling. Second, we now have the capital ST instead of the small s. This indicates a particular sample of state at time t, whereas small s is a random variable. So that's a stochastic gradient descent. So for gradient Monte Carlo, you simply use the Monte Carlo target G, that's the return, as unbiased estimate of the v pi. And at every step, you will update the W based on using GT to replace the ground truth v pi st. Remember, GT is a return from current time step until the end of the episode. So that's gradient Monte Carlo, and also we can use TD. So TD uses a parameterized value function to approximate the true value function v pi, and you're trying to learn a mapping from a state to the target value, which is next step reward plus next state value times gamma. So now the target is dependent on W. It's non-IID, independent and identically distributed. So I mentioned this before during imitation learning. So this compared to supervised learning, say you're mapping from pictures to labels, and you have a fixed set of training data set. X may be an image, Y may be a label of a cat or dog, and these are not affected by your weights. So they're there, they're static. Whereas for TD, your target is changing as you update W. So it's really a moving target. So for TD, you are using the TD target as a biased estimate of v pi, as opposed to the G for Monte Carlo, which is unbiased. So now, if you're taking the gradient of this squared error in a sampling approach, a particular sample of st plus 1 and rt plus 1, you cannot simply take the gradient inside and do this, because this term here is dependent on w. That's the non-ID part. So this gradient is not equal to 0. However, we pretend it's 0 and simply do the call it a semi-gradient. So yeah, this is the right. So if you remember the gradient Monte Carlo, stochastic gradient. So at this point, when you are from here to here, you can v pi is not dependent on w. That's the ground truth value function. And taking gradient over with regard to w does not affect v pi. So you can just take it outside and move the gradient inside. But here, this guy, the target here, is dependent on w. So we cannot move it inside, strictly speaking. So there are research that does the gradient TD. You can take the gradient on both terms with the chain rule, and there are some results. But this more common approach is semi-gradient. That is, you pretend this first one does not depend on w, even though it does, and just take gradient over the last term. So semi-gradient, because it's not a true gradient, it may not converge to the local minimum, but it converges faster than gradient Monte Carlo due to more frequent update per time step instead of per episode, and less noisy updates, less variance. So the semi-gradient TD solution may be stuck in here, so it may not reach the even the local minimum. So with a linear function approximation, so we're not yet discussing neural networks, which is a non-linear function. Let's first try linear function first. So the value function is a product of weight and the feature vector. So the transpose notation just says it's a horizontal laid out vector. Without a transpose, it's a vertically laid out vector. So if you have a feature vector of size 2, then this value function is this w1x1 plus w2x2. So that's the same state with two features, and taking a derivative, taking a gradient on w gives you this. It simply returns the vector x. So semi-gradient with linear function approximation simply has x on the right-hand side. That's the feature vector. Whereas before, we had this gradient operator applied to v hat. But here, v hat is a product of two terms. So it's simply x. So it's step size alpha times TD error times feature value. Notice it's a vector notation for both w and x. So there's a theorem that relates linear TD's fixed point and minimum of value error, which is less than or equal to 1 minus gamma. So it's a non-trivial theorem. So if gamma is large, that is, you're looking a long time into the horizon, then error of TD may be very large. If gamma is very small, you have a very short, nearsighted view. Then the value error of TD can be very close to the true minimum. So tabular TD is a special case of linear TD by using a one-hot encoding of states with 1 for the ith element and 0 for all others. So for example, if you have two states S1, S2, you just have two features to recover the tabular TD case. One feature is 1, 0. Another feature is for S2. The feature for S1 is a vector of 1, 0. Feature for S2 is a vector of 0, 1. And then the value function for S1 by the definition is equal to W1. A value function for S2 is equal to W2. So the features simply pick out the corresponding weight for that state. So it assigns a value to each individual state. That's the tabular TD. So if you work out the semi-gradient TD, it's same as tabular TD, except using the value function form instead of the table form. But the value function form we saw before is just the particular weight, so it's the same. So tabular Monte Carlo is also a special case of linear gradient Monte Carlo. So in books chapter 10, it talks about on-policy control with approximation. We saw this figure before, generalized policy iteration for tabular setting, updating the Q for each SA, each iteration, based on a table. But for function approximation setting, it's essentially the same, except you use QW, which is really the Q hat here, as a function approximation instead of a table, and you update the W parameters, which affect the Q hat in each iteration. Other things are all the same. So for the updated equations, if you have recall Sarsa and semi-gradient Sarsa with function approximation, simply replaces the capital Q, the tabular version of a Q value for state action, with the Q hat, the function approximation for it. And you have, oh, okay, yeah, I should also highlight the difference is you also have the gradient term on the right, which is extra compared to the tabular setting. And for expected salsa, similar. Q-learning, similar. Yeah, just a simple replacement. And you can use linear function approximation as Q functions. So W times X SA instead of W times XS. So you can replace the gradient term with X with the linear function approximation. So that's the end of the short chapter on function approximation. Any questions? Okay, so I have the last chapter 11 on policy-based methods. So I put a sign here, not covered in exam. So we have been discussing value-based methods. So you learn the value function, particularly the Q value function, and then the policy is obtained by taking an argmax, often implicitly during training. So could be epsilon greedy. Policy-based, there's no value function. You only learn policy. And after critique, learn value function and also policy. So policy-based RL, the pros are that it's effective in high-dimensional or continuous action space. So value-based RL is only applicable to discrete action space. It's inefficient to discretize continuous actions for high-dimensional action space, as taking argmax may be expensive for very fine discretization. Can learn stochastic policies. So value-based IL learns a near deterministic policy, either purely deterministic with the greedy action selection or epsilon greedy, which is near deterministic. But sometimes, for example, for the game rock, paper, scissors, deterministic policy does not work well. So and policy-based IR converge better convergence properties. We saw before, right? The policy becomes stable long before the values converge. The disadvantages are that it typically converges to a local rather than global optimum, and evaluating a policy is typically inefficient and high variance. So here's the mountain car example. So the value function, position, and velocity are the two elements in a state. It's quite complex with lots of different, yeah, it's not smooth at all. But a simple policy that works well is to accelerate in the direction of current velocity. If velocity is to the right, you accelerate to the right. If velocity is to the left, you accelerate to the left. So actually, that's a pretty good policy. This shows the simplicity of policy you don't have to learn the very complex value function in the middle. So function approximation for value function, we typically use the convention of W as the parameter for the Q or V value function parameters. And then we use the theta as a convention for the policy function parameters. So this pi a given as theta denotes the probability that action A is taken in state S with a parameter theta, and it's as a probability, it's always positive or 0, and it sums to 1 for all actions. So here's the example to illustrate the stochastic policy. So here, the example here is a partially observable MDP, which means that the agent cannot observe its position directly. It can only observe features of the following form. That is the indicator function, wall to direction 1, direction 2. So uh, so yeah, I should put if there are walls in each direction. So it can only see the walls, but it cannot. It doesn't have a GPS to tell it exactly its coordinates. So therefore, it can tell that it's in here, right? Because in this position, there's a wall to the north and to the west. This position, there's a wall to the right and to the north. This position, there's a wall only to the north. And these two positions, there are walls to the north and south. So these two positions are indistinguishable. The agent cannot differentiate between these two gray states. Therefore, it's a palm DP. The environment is not fully observable. So for a value-based IR, you can use a function approximation to encode the value Q value function. And for policy-based IR, you can use G function to approximate the policy function. So so for a deterministic policy, because you cannot distinguish between these two gray states, they must have the same action for deterministic policy. So either move all to the left, or move to the west, or move to the east in both gray states. Either way, it can get stuck and never reach the money. So and there's a loop here. You can get stuck in this loop. This is good, but once you are in here, you're stuck. And vice versa. If you go right, go to the east, one of the states will get stuck. So it may traverse the corridor for a long time. If you have epsilon greedy, then it may have a small chance of getting out of the corridor. But for a optimal stochastic policy, that is, you at each of the gray states, you move to east and move to the west with same probability. Once you have walls to the north and south, that's these two states. And then this random move in the gray state will let the agent reach the goal state in a few steps with high probability. So this just shows that the optimal stochastic policy is much better than optimal deterministic policy. So if you have a good memory, you'll say that this contradicts what we discussed before, right? What we said before is that the deterministic policy, optimal greedy policy is always better than the epsilon soft policy. So this is only applicable to MDP, not POMDP. So if the agent can see its exact location at every step, instead of the features of walls on either side, then it can have a greedy optimal policy. But for POMDP, the greedy policy cannot is not good. So one possible parameterization of the policy is the soft max, which is this formula, where H is the action preference, which may be a linear function or a deep neural network. So this sum obviously sums to 1 for all possible, sorry, this is action, sum over A, for all possible actions. As compared to epsilon greedy, so for epsilon greedy, only the top choice, the greedy choice, has a high probability. All the other actions have equal low probability. So that's not very accurate. So if you look at these middle two action values, they're very similar. So there's really no reason to assign the third one very low probability. So the softmax, this proportional assignment is more reasonable. And the Gaussian policy assigns the action probability with a normal or Gaussian distribution. So mu is the mean of the Gaussian, the center point of the Gaussian, and the variance sigma represents the how sharp or how flat the Gaussian is. So the sharper the Gaussian, the more deterministic your policy is. So here's an example MDP. So to introduce the average reward. So here's the MDP. So every action has 0 reward except these two. So if you have always left policy, then you can compute the value for the state S as a 1 reward plus 5 steps later, you have another 1 reward with a discount factor gamma, so gamma to the 5th power. And then you have 5 steps later, another 1 reward, gamma to the 10th. Eventually, you have 1 minus gamma to the 5th based on geometric series sum. Or you can compute it with a recursion with the same result. So for the always right policy, you travel 4 steps and get 2 reward. So the first reward is 2 times gamma to the 4th power. And next one, you have additional gamma to the 5th discount over the first reward. And the sum is this. Or you can use the recursion. So the optimal policy depends on the discount factor gamma. So the table shows that if gamma is 0.5, the left is a better policy. Always left is optimal policy. If gamma is 0.9, then always right is optimal policy. When gamma is equal to 0.841, then left and right policies are the same. So if cycles are longer, say each with 100 states, then gamma is 0.993. So this so if you have to learn this policy in a without the model, then it may be difficult to learn with the larger gamma and longer chain, as opposed to the simple analytic solving approach for known MDP. So that's why. So this is the average reward, as opposed to the cumulative discounted reward. So it's the sum over the expected reward within the horizon h, and h goes to infinity. So let's parse it one by one. So the first term here is the expected reward if we start in state S and take action A, taking expectation over all possible S prime and R. And the next expectation is over the all possible actions from state S. And next expectation is the average reward under policy pi by weighting expected reward of each state S under policy pi with mu pi, the fraction of time spent in state S under policy pi. So this particular definition measures the rate of reward or reward per time step for a given policy, averaged over all states. So if you compare this to the Bellman expectation equation for a state value function with a cumulative discounted reward, the differences are first, this is different. So because average reward is one-step reward average, we're not adding the additional future term. And also this part is different. So this average reward is over a policy for all states, averaged over all states, whereas this V pi is for a single state. So the differential return is the sum over all the reward, every step of the reward minus the average reward. So it measures how much better it is to take an action in a state than average reward under a certain baseline policy pi. It's used to compare actions if the same policy pi is followed on subsequent time steps. So compare this with the regular MDP with a discount factor gamma on the top. Yeah, it should be here. So the differential return for this MDP. So first, we can get the average reward of left action is 0.2, which is 1 reward every 5 steps. And for the right action, it's 0.4, which is 2 reward every 5 steps. For policy always left, so you can compute the Q SL, the left action, and then follow the pi L forever. So that's 1 minus 0.2 plus 0 minus 0.2 4 times plus 1 minus 0.2, which is 0.4, is called a Cesarean sum. For the right action, you take the right action first and then follow the pi left forever. But you only have a choice at the state S. You don't have a choice at the other states. So you take the right action for one circle, and then you go around the left circle forever. And then its reward is 0 initially, and 0, 0, 0, 0, and then you get a 2 reward. And finally, you follow the left policy, follow pi L, which is computed as 0.4. So you get the 1.4 as the reward for the right action. So the optimal action by the greedy action is R. And then if you take right action and follow pi R forever, you can get this sum is equal to minus 0.8. And take left action, follow pi R forever, you get minus 1.8. So again, the optimal action is R based on differential return. So how do you get the Cesarean sum? Here's the Grandis series. So what is the sum of this sequence, infinite sequence? One view is that it's 0 by grouping this way. Another view is that it's 1 by grouping this way. Another view is that you can write it as 1 minus itself. So it's a 0.5. So they all seem reasonable, but which one is correct? So Cesarean summation is defined as limit into infinity the partial sums averaged over the number of partial sums. So if you have n equal 1, then the partial sum is 1 divided by 1. If it's 2, it's 1 plus 0 divided by 2. If it's 3, it's 2 over 3, and 4, and 5, and 6. So this sum eventually converges to 0.5. So this view is consistent with the Cesarean sum. So this is how you get this infinite sum over here, 0.4, by performing the this procedure of averaging the partial sums. So for the average reward, you can also write out the Bellman equations, Bellman expectation, and Bellman optimality. So if you compare with the Bellman equations we saw before, so the only difference is that, so the 4 Bellman equations we saw before, 2 expectation equations and 2 optimality equations, you simply replace all the rewards by the difference between the reward and the true average reward. And you remove the gamma. There's no discount factor. So having introduced the average reward objective, now we want to try to maximize the expected average reward for a given policy by adjusting the parameter theta. So this is policy gradient. Now, we want to use gradient ascent because now we want to maximize our pi. So you take the gradient of this definition of average reward, and then you're stuck here. You cannot move the gradient inside the expectation over mu pi, since it depends on the policy parameters the theta. So modifying the policy pi changes the distribution mu pi. So if you contrast this with the gradient descent for optimizing the value function under a given fixed policy pi, we saw before, you can move the gradient operator inside the expectation over the states, because the distribution mu pi is not dependent on the value parameters w. So you're optimizing the v hat function. And that's a function of w, but mu, the distribution of state, is based on the fixed policy pi. So it's not dependent on the value function parameter w. But for the policy optimization, this mu pi is dependent on the policy pi. However, there's a policy gradient theorem that says you can put the gradient inside as long as you have the q pi at the end. So compare these two. You cannot move the gradient operator inside directly, but if you have this q pi on the right, it's okay. So it's a non-trivial proof. So once you accept this theorem, you can use the policy gradient to maximize. So for a given state S, for this inside term, it maximizes the average reward in that state. And averaged over all states, it maximizes the overall average reward by updating the parameter theta with, now it's plus, it's gradient ascent plus a alpha times the gradient. So SGD is this. So instead of the expectation, we perform the sampling. So here's an example. Suppose you have a policy, maybe a softmax, maybe some other distribution. So at this point, you have the Q value here, and then you compute the policy based on the Q, maybe by softmax. So at this point, yeah, it doesn't really correspond to the figure. Yeah, let me delete this text here. Yeah, just to see the image. So if you perform gradient ascent after a step, say you've seen the reward on the lower right corner, then your policy will be updated to increase the probability of moving right and down, and decrease the probability of moving up or left. So that's the effect of updating the parameter of theta. Theta is a vector. So for a policy gradient, so by performing, we want to evaluate this gradient by sampling. So the outer part of expectation over states with the distribution of probability of state in a under a given policy is expectation of pi, and the inside is summation over A action. So it's not a really a expectation. So expectation is summation over A times the distribution probability of A, and then times something else. So this part is expectation over A. But just the summation without the pi of A's distribution is not a expectation. So to evaluate this policy gradient with SGD, we turn it into expectation by multiplying with pi and dividing by pi. And then this guy turns into a log, a gradient of a log. And this guy is the same. So by adding, multiplying and dividing by the pi, we can replace the action variable expectation over action by sampling by the particular sample capital AT. So the SGD update is this formula. So every update, you have parameter alpha times gradient over log pi. This guy is called a score function. And on the right, you have the action value function. So I think in here, yeah, it's not really a SGD because you need a summation. So yeah, so this is still difficult to evaluate. But once you do the transformation now, you can evaluate it with sampling. So this is SGD. So the actor critique algorithm, so we saw this formula before, the Q pi. The Q pi, if you had all the Q values for every state, then it's nice. But what if you don't have it? Then you can use the actor to evaluate this Q by this TD error. So the red part is the TD error. So this, we're still in the average reward setting. So we have the next step reward plus gamma is 1. So we simply add the next state value minus the average reward, and then we subtract the v hat, which is the baseline reward, to reduce the update variance. Because this guy, if you take expectation over the policy, it averages to 0. So adding it, subtracting it does not make a difference. So this simply says that we're just evaluating. So after we take any action AT in state ST, critique this guy uses the TD error W delta T to decide how good the action was compared to the average for that state. If it's better than average, delta T is higher than 0, then actor updates the policy parameters to increase the probability of AT in state ST, and vice versa. So we're not, we really care about the ranking of different actions in every state. We don't care about the absolute values. So subtracting the average makes no difference on the ranking. So on the figure, it shows that at every time step, the critique gets a reward, updates the TD error, the TD error is used by the critique itself, and also by the policy, the actor, to update the policy. So actor and critique learn at the same time, constantly interacting. The actor is continually changing the policy parameters theta to exceed the critique's expectation, and the critique is constantly updating its value function W, parameters W, to evaluate the actor's changing policy. So here's the actor critique algorithm. So it computes the critique, computes the TD error delta, and then the actor uses the critique uses the TD error itself to update its weight parameter W with semi-gradient TD. An actor uses also this data to update its policy based on policy gradient. So as a result of this interaction, they both get better and better. So actor gets better policies, and critique gets a better estimation, better value functions for the new policy, because the policy evaluation, the value function is a policy-specific value function. So suppose you have a softmax policy. So this is the softmax policy with a linear preference function. So the h here is a linear function. So here I think x is also a vector, so it should be a vector. So the critique update is this formula we saw before. When you substitute the linear function here, is simply the multiplying by the state vector. And the actor updates this equation here. This gradient is a little bit messy to compute. Critique is this. Actor is, no, I think I got it not really. So this shouldn't be, this is redundant, yeah. Yeah, so I have this slide in a different order, so it should be here. So this just shows you how to take the derivative of the log policy. Now this guy, log pi, so if it's, so now both the mean mu and the variance sigma is parameter of is a function of the theta parameters. So if you take a derivative with regard to the theta mu, this is theta mu, and on the bottom you have theta sigma for the variance. And then you can use the chain rule to work out the derivatives and eventually get this yeah, I think get this one. Okay. So there are many variants of policy gradients. Mainly, so this term on the right of the policy gradient could be, we saw this Q pi as the actor critique. Actually, I think what we saw before was the advantage actor critique, which is Q pi minus the value and then you have a TD actor critique. So all the variants are possible. So this is an example. So by the way, all the slides are from a Coursera course from University of Alberta. So the continuing task of pendulum swing up. So you have a state of beta, which is this angle relative to the up direction, is minus pi to pi, and the beta dot, the angular speed, is arbitrarily specified as minus 2 pi to 2 pi. So this is just a user imposed range for simplicity. And action is either no action or the torque is to swing it in the clockwise direction or counterclockwise direction. Reward is minus a beta absolute value. The goal is to set the pendulum pointing directly up and keep it that way. So the value function is the linear value function for the critique. And then for the actor, the preference function is also linear. And then we set the critique, update the critique at a faster rate than actor with the alpha parameter of actor smaller than the critique. So there are some performance results. So why do we have continuous actions? So the one we saw before, we have discrete actions, 3 possible actions. but it's often desirable to have continuous actions. So it may not be straightforward to choose a proper discrete set of actions. So continuous actions allow us to generalize over actions. So if an action is good, its neighboring actions are also likely to be good. But discrete actions lack generalization, so each action is independent of others, including its neighbors. So similar to value functions for discrete states. So if you have a Gaussian policy for the pendulum swing up example, say you have a continuous range of actions, acceleration, angular acceleration, from -3 to 3. Then you may have a Gaussian policy with the mean defined as a linear function and variance defined as the exponential of a linear function. So, and then during the policy gradient, during the actor critique learning process, you gradually the policy gradually reduces the variance and eventually converges to a deterministic policy. That's a typical training process of actor critique. Yeah, I think that slide was should belong to here. So this is the process of taking the gradient for this Gaussian policy, where the parameter theta appears both in the mean and in the variance. So this is in the textbook also. So here is the summary of function approximation. So if we are using average rewards, then we can use the different variants of actor critique. If you're not using average reward, then we use the cumulative discounted reward. Then we can use, if it's your learning per episode, you use gradient Monte Carlo. If it's using learning per time step, if it's not a control problem, so you're doing policy evaluation, use a semi-gradient TD. If it's a control problem, you use SARSA Q-learning or expected SARSA. Okay. Okay, so is everybody still here? Did you go to lunch? Go to dinner?
I will go for dinner now. Yes.
Yeah. So that's the end of all the lectures. As I said, so the exam will cover lectures 1 to 10, and also the lectures by color, which is the 4 PDFs. So yeah, as I promised before, I'm gonna share some sample exam questions, which I will release hopefully tomorrow. So any comments by Carla on the last lab?
Yeah, I can say I just sent an email. I recorded some videos earlier today with some how to install PyCharm and how to run in Colab if you want to store the files from this car racing, and this is not obligatory. But I've also quickly graded number 4, so I think most of you who have done lab 4 has got your points. There are still 2 missing for lab 3. And yes, someone asked me about if you need to register for the exam. And as I understand from you, Songwai, you don't need to do that.
Right. The exam will be based on Canvas. So the exam time I have announced on June 1st morning. So it'll be here. Quizzes. I'll release it on the exam time, so you can answer it here.
Okay, so no list is needed, so anyone can join this quiz exam.
So yeah, for Thursday's class, I will hold a Q&A session. So I'm a little worried that there may be no questions. So just a free discussion period, I guess. Yeah, unless you have a better suggestion. But I think just the yeah, the materials are a lot, so I think it's not realistic for me to give a review lecture. It's hard to cover all the past material, so I just do a Q&A.
Yeah, and please send some questions to us if you have some particular question you want to answer, and too shy to ask it. So, and then we can prepare a good answer as well. So no more questions or nothing? Well done, Sangwa. You have spoken a lot during this course.
Well, I certainly enjoyed teaching it. I hope it's not a torture for most of the students.
Yeah. Yeah, so it was interesting, and I think it was good that I made some easy overview labs and short lessons, and then you took the details for those to get a more deep understanding of what's happening and so on. And also the car part, I didn't participate on all those first parts, but there were quite many. So I don't know how the course contents, and it's a lot about reinforcement learning, but it's also a lot about cars and vehicles and so on.
You mean the first half of the course?
Yeah, exactly. So don't forget to read about that as well.
Yeah.
Students.
So, yes. Okay, so I guess I'll let you guys go to dinner.
Yep. Thank you.
See you on Thursday.
Yep.
Goodbye.
Thank you. See you.
Thank you. Bye-bye.
Thank you. See you Tuesday.
Thursday.
Thursday. Yeah.